My name is Oleg Anastasyev. I am principal engineer in OK.ru. OK.ru is one of the most popular social networks, not only in Russia. Here you can see our top 10 countries by audience. There's a lot of functionality expected nowadays from a social network. So from the engineering perspective, OK.ru consists of 6,000 hardware machines running more than 15,000 tasks. These tasks are running either directly on the hardware or in containers in our 4 private clouds. These tasks provide more than 300 unique performant microservices. And now we'll try to build one of these services together, a messenger or chat service. So in a typical messenger, a user could have a list of conversations or chats. An average user actively participates only in a limited subset of all these conversations. Our stats show that only 5% of conversations generate 95% of requests to the service. Most of what data messages store are, well, messages. In most cases, only up to 13 of freshest messages are seen, and so being requested from the messenger's data store. But this doesn't apply them getting the freshest message of each conversation to render it next to chat name here. These messages are unlikely to be requested for the second time. When rendering a web UI, freshest message is retrieved for each conversation shown to user. For mobile UIs, all conversations stored on user's device. Let's aim to store at least 500 billion messages in, say, 5 billion conversations. These could take about 100 terabytes of data, not counting a replication. This new service should be fast enough to handle more than 100,000 reads and 8,000 writes per second. Every modern messenger should have full text search function, so when some such text is entered here, we'll find conversations and messages containing it. And this means that messages should be reiterated to build a search index. Messages have not only text. Here we can see some simplified message table with the conversation ID here, ID of the message within conversation, the author of the message, the message type, and finally the text of the message, and a list of file or picture attachments to the message. So messages in our service can be represented with the table like this one. A messages service must implement the following operations. getMessages gets messages in the specified chat for the defined user. It can return different messages for different viewers because of the selective message deletion, appropriateness filters, and so on. That's why the viewer is among parameters to this method. Most of requests to the messenger service come to this method, so it should work as fast as possible. getLastMessages gets a single last message for a supplied list of chats to render the freshest message for each chat in the conversations list. This one is the most heavy operation of the service. Numerous chats should be traversed to get the last message of each one. Add operation adds a message to some conversations. Search is a full text search in users' conversations. indexMessages operation builds an index for the search to use. Let's try to build this messenger service, employing the modern microservices architecture, of course. So users using their mobile phones or web browsers, either directly or using some front-end servers, communicate with the messenger service. This messenger service runs application logic for the service. The application state or data is stored separately in the dedicated database store, and it's fault-tolerant and highly available, of course. To achieve this, database could do some form of replication, so it's distributed, replicated, and so on. But let's leave it out of scope for a while for simplicity. That's it. Let's go to try to go live and see how the most frequent operation getMessages could be implemented. To get it done, the query like this should be executed by the database. The problem here is that this query should be executed 100,000 times per second by the database, which generates some load to the service. And well, scaling is what microservices are all about. Let's start more services, more instances of the service. And now we see that instances of the service generate more requests to the database, and now the database is overloaded. What next? We could either scale the database or make use of the knowledge that only 5% of data are hit by majority of requests. Let's cache some. And database definitely has cache we can configure. But it turns out that the database cache is not effective enough. It caches a lot of unused rows. This is because other operations of the service, the getLastMessages operation and the message indexing process, are reading not only 5% of actively used conversations, but all 100% of conversations. These operations are very rare comparing to the getMessages, but because they touch all conversations, all of them hit the database cache, flooding it with all those 95% of rarely accessed and useless cache data. The database cache is typically restricted by a few generic algorithms, like the least recently used algorithm, for example, and typically can be adapted for application logic to control which data should be cached and which should never be. So either we should throw much more memory to cache all this rarely accessed data in the database cache, or be able to implement an explicit cache management in the application logic of the service. So only messages which should be cached are cached. Let's introduce the memcached service for this purpose. This takes load off the database. When the load increases, we can scale memcaches independently from service instances and the database. Thus, we came to the typical modern service architecture many of us are familiar with. So let's delve into costs hidden in it with more detail. So first is the CPU cost of the marshalling and unmarshalling. This is the process of transforming the memory representation of an object to a data format suitable for storage or transmission. To make a single request to the memcache, the application logic marshals the request and its parameters. Then the memcache unmarshals this request to its own in-memory representation. After the memcache processes the request, it marshals the response. The application then unmarshals it. These marshalling costs also apply for the application communication with the database. Intuitively, we tend to think this cost is negligible. The right thing to do is to measure it for the exact system of costs. In this talk, I'll use measurements and results published in the excellent paper named Fast Key Value Stores, an idea what time has come and gone, from the group of researchers from Google and Stanford University. Please read it if you are interested in how these measurements work. So according to these measurements, this cost could be up and more than 85% to CPU load and can add up to 27% to median latency of the system. The second is the cost of overreads and overwrites. These are costs of reading or writing more data from the cache than it is necessary. If we stored last 13 messages in the memcache packed into a single blob for each conversation, to render this list with a single freshest message next to each conversation, we'd read a blob containing all 13 messages for each conversation, marshal it, transfer to the application, unmarshal it to individual 13 messages, and throw away 12 of them except the freshest one. In the same paper states that if only 10% of the data is used from all the retrieved data, like we have here approximately, we can expect up to 46% of CPU and 86% of the network traffic wasted by overreads. The third is the cost of network-related latency. Each request-response pair to both the memcache and the database introduce the round-trip time latency, or RTT. The additional delay adds up for moving the data over the network to or from the memcache and the database, and can vary a lot depending on the size of the response. But the worst thing is that these latencies are multiplied by the number of network requests the application logic makes to serve a single user's request. For the getLastMessages request, a separate request for messages of each conversation must be made to memcache, making tens or even hundreds of requests. Well, as we can see, costs are high, but how can we lower them? Most of the load naturally fall to the memcache and its link to the application logic. So these costs are much more visible here, and most efforts in industry are spent on optimization of memcaches and their link to the application logic. For instance, Redis and Tarantul are trying to fight overreads by introducing data structure in the memcache, allowing application developers to request only the necessary subset of data. Netcache fights network latencies by introducing the in-network caching embedded to the network switch infrastructure. KV Direct is about to lower CPU costs by placing a marshalling onto the network interface count. We'll try to optimize it a bit from the different angle. These costs are introduced by sole remote location of the application state, so we can get rid of them by moving the state closer to the application logic. This way, we came to the idea of stateful microservices. A stateful microservice combines the application logic with the custom in-memory store in the memory of the same single process. So network latency costs are not applicable here anymore. This in-memory store is custom. It has the application-specific logic implementation. This allows an application developer to implement a service application logic without overheads. CPU costs of marshalling could be eliminated or lowered significantly, selecting the appropriate application-specific data format for both companies. Embedding distributed persistent store code to the same process eliminates same costs on the second leg of the architecture and allows us to easily integrate all components. Words embedded and distributed next to each other could be a bit of mind-blowing. What I mean here is that we embed the code of the distributed store, so this code runs within the same process. An instance of stateful service then becomes a normal node of distributed store, participates in distributed store clusters, stores data on the local machine's persistent disks, and does all the necessary operations just like a dedicated distributed node could do. This way, we've got a more efficient stateful microservice, and it always is more efficient than the same application implemented as a stateless microservice because it has no more costs to pay for the external location of the application state. Let's also see how the statefulness affects the fault tolerance of the service. For this, let's consider what distinct failure scenarios could be in the simple distributed system of two communicating participants, the client and the server. The client sends a request message, the server processes a request and sends a response message back. The client can send a request and disappear from network. The server can disappear as well. They can crash or reboot, or their hardware can fail and hang. A request or response message could be lost. The network is failing, buffers overflow on either communication party. The server could time out. A response is sent beyond the defined time bounds. The invalid value response, the server responds with a message the client can't understand. How could this happen? Easily. The server is running fresher version of the software, but the client runs obsolete one. And finally, the arbitrary or Byzantine failure. A body makes arbitrary messages at an arbitrary time. This could be some bad intention actions like DDoS attacks, it could be bugs in code, and so on. I discussed these scenarios in more detail in my talk, Distributed Systems at OK.true. Here goes the link in the footer. Go read it. So, a total of 7 failure scenarios are possible. Let's try to apply them to both stateless and stateful architectures. Let's take a look at a stateless service first. A user sends a request message to the application service, and the service processes it, sending requests and getting responses from both the memcache and the database over the network. So here we have pairs of simplest distributed systems. The first one consisting of the microservice and the memcache, and the second one, the service and the remote database store. What makes things worse is that failures to this memcache and the database are not unrelated to each other. So we must consider how failure to the memcache will affect part of operations working with the database, and the other way around, how failure of the database affects data in the memcache. So these failures are bound to each other and must be explicitly addressed by an application developer. So we have 7 failure scenarios here, another 7 to address here on the database, and we have third distributed system here between user and the microservice itself, with yet another 7 failure scenarios to address. All of these failures are bound to each other, so an application developer must address all of them, plus their combinations, when a failure in one component affects operations or state of another. This adds some complexity to the code, making such failure handling hard to implement and debug. Let's now take a look at the stateful architecture. There are same 3 machines, but their layout would be different. The sharding scheme would be different as well. For the stateless architecture, each of 3 machines is responsible for some set of keys K. When going stateful, each of the machines is responsible only for 1/3 subset of the original key set. each for its distinct subset. A user communicates directly to each stateful service instance, making the same 3 pairs of communicating parties. On each of them, the same 7 failure scenarios are possible. The only difference is that these scenarios are unbound to each other and not unique, because all 3 instances are implemented as identical components. So addressing failure scenarios here is easier. Such failure handling can be implemented uniformly for the one pair and will work the same way for all others. To further evaluate reliability, let's compare probabilities of the full downtime. For the stateless service, downtime of any component, the memcache, the database, or the service itself leads to inaccessibility of all keys from the set K. So the probability of the service downtime for keys, for all keys from K, can be calculated like this. For the stateful service, downtime of a single machine leads to inaccessibility only of a 1/3 of Ks. So when all 3 machines go down, each one with its own 1/3 of K, there will be an accessibility of the full set of Ks K. So the downtime probability for the full set could be calculated like this. Which one is better is not obvious, looking on these formulas. So let's try to evaluate them, these numbers. Let's assume probability of a single machine downtime is 1/10. This is very high probability, of course. In real life, there are much smaller than 1. But let's take this number for simplicity. Then we have these numbers for downtime probabilities. The smaller downtime probability is better. We see that the downtime probability of a stateful service is orders of magnitude smaller. In real life, people use the replication to reduce downtime. So let's set up replicas for each of the components on the left. Installing the second replica reduces downtime probability of a component by an order of magnitude. So we have allocated 6 machines for the stateless service. Is this setup more reliable than 3 machines from the right? Let's do our calculations with new numbers. Actually, no. Failures are still bound to each other, so both replicas' failure will still lead to downtime of the full case. Let's try with 3 replicas of each component. A total of 9 machines against the same there on the right. Nope. The same replication idea could be applied to stateful service as well. And this makes downtime probability of 1/3 of K smaller by an order of magnitude 2, and downtime probability for a full set by 3 orders. So as we can see, stateful microservice is more reliable. Okay, let's go to the implementation of this idea. So what to start from? We want our service implementation to be highly available, so a replication must be supported and consistency guarantees between replicas must be defined. And we want our service to be scalable, so when load to our service increase, we could scale it by adding more instances. Now our application and its state are collocated, so it must implement resharding of the state's data among newly added instances. All these could be implemented, of course, by ourselves, but it is better not to implement this from scratch. These parts are really hard to get right. Instead, let's find something ready to use. All these words, replication, consistency, guarantees, and resharding, give us a hint to seek this in modern distributed databases. So first of all, let's decide which one's code we would embed. This database must be implemented in the programming language of the application logic to make a code reuse simpler, avoid partitioning costs, and simplify an integration of components. It also must be open source, so necessary extensions of a database functionality could be implemented. Okay, .ru mostly use Java for our applications. We had successful experience running Cassandra database, so we choose it as the database for embedding. The first step to embedding Cassandra is launching it in the same JVM together with our applications. Looking at its startup scripts, we could easily find the Cassandra daemon class. It manages life cycle of a node. So all we have to do is include necessary libraries to the class path of our application and start the Cassandra node by this code. Cassandra.yaml here is Cassandra standard configuration file. That's it. Now we have the database node running in the same process. When started, it will read its configuration and join the Cassandra clusters just like if it was started by standard startup steps. So now we have the state collocated with application, and let's look how it changes the client request boundary. So here we have our user. His name is Luke, and he is about to participate in conversation which key falls into some set B. Luke uses some front-end system for this, that's why I rounded him with a green rectangle. For the stateless service, there is no difference to which available instance to send a request to. The front-end could make a request to this instance or to these instances. For all these instances, cost of serving a request of a key from the set B is equal. Some network requests must be done to remote memcaches and databases to get the necessary application state. Contrary to stateful services, every instance has some part of keys stored locally. Leftmost instance owns some set of keys A, second owns B, and the rightmost owns C. This way, the instance owning the set B does not have to make a network request for the data. It is either in the memory of the instance B process on it, or it can be read from its disk. Other instances cannot access B's data locally and have to make network requests for it. The cost of processing B's requests are higher because now should include costs associated with the marshalling and the network latency. So to make the processing effective, clients must route their request directly to the instance owning necessary data and avoid routing their requests elsewhere. This is possible if clients are aware of the cluster topology. I mean information about states data partitioning across cluster nodes. Such client routing could be implemented on the front-end system in a form of library. This library routes requests directly to nodes owning appropriate data partitions, so these nodes can process requests accessing the local data only. The data partitioning is a sole responsibility of a database, and we have the Cassandra code embedded. Let's take a look how Cassandra partitions data. Let's take a look. Every row in Cassandra has a primary key composed of two components. The partition key is used to determine the node owning the data. The clustering key is used to define the order of rows within a single partition and has nothing to do with the data partition. Rows with non-matching partition keys fall into different partitions and could be owned by different nodes potentially. Rows with non-matching only clustering keys are in the same partition and will be placed to the same node ever. As in the messenger application, order of messages within the single conversation is important, but order of different conversations between each other is not. We select the conversation ID as a partition key and the message ID as a cluster key. There are following components in the Cassandra code responsible for the data partitioning. The partitioner gives them the partition key, calculates its token, usually applying some hash function to it. All possible token values are usually depicted as a ring. The partitioner is defined for the cluster once and can be changed in future. This whole ring is then split by token ranges. Mapping of ranges to primary nodes is stored in token metadata. And the final component is the replication strategy. It defines how to select nodes for secondary replicas of data and how many of them should be at all. Different replication strategies could be configured for different tables. That's it. This information is enough to get mapping of all data to cluster nodes via this simple coded snippet. The endpoint map here is exactly this. It maps max token range value to all replica nodes addresses. Transferring this map to the client, the partition-aware routing can be easily implemented. Also to consider is that this topology is not constant and can change over the cluster lifetime. Some new nodes join the cluster, some old nodes leave. So this map refresh should be implemented on clients, as well as dealing these clients with the not yet refreshed stale mapping information. Here, various strategies we could choose based on what suits our system most. Well, clients now wrote their request for the data to the right nodes. Let's look into how these nodes work with their data. So, messages are stored in kind of this table, and we are about to implement getMessages to get list of messages within a conversation. So it should execute a query like this one. To execute this query using DataStax Cassandra client drivers, we should use a code like this. You can find this code on the Getting Started manual on the GitHub page. So in the first line, a connection to database cluster is established. The second line sends a query over the network and retrieves a result set. In third line, data is used, and connection to a database cluster is closed. This is hidden in the final part of the try with resources statement. In real life, this could be more complicated. Management of connections, their configuration should be retrieved from somewhere, some connection failure handling should be in place, and so on. To execute the same query on an embedded Cassandra, we call this class execute method. It executes a query with the specified consistency level, binding specified values to query parameters, and returns the same result set. Please note that this method is static. There is no connection information, no any cluster configuration passed in parameters. That's because an application code is working in context of a database and has of a database it has embedded. So database to connect to this is not, there's no database to connect to. This instance is the database. Accordingly, messages for our getMessages implementation could be retrieved from the embedded database by this code. To add a message, a query like this should be executed, and this code is even a bit simpler that we would write using the original database driver. Okay, let's move to the implementation of custom in-memory message store. Let's start with approximating the volume of data it should store. The total amount of data is about these numbers. Only 5% of conversations are active, and only 13 messages of every such conversation should be stored in memory. Okay, now we have all the data and can calculate that a fair amount of them should be reside in memory. These numbers should be further divided to a number of nodes in cluster and be multiplied by a replication factor. Let's recall the list of all requests the messenger service should implement. Only first 3 methods work with active conversations, so the new in-memory store should implement only these 3. Others touch non-active data and can flood memory with the relevant rows, as we discussed earlier. Let's implement getMessages first. A user named Leah opens the messenger and selects the conversation with Duke. I mean the frontend sends getMessages request for the last messages in this conversation. The application logic looks for cached conversation in memory. Well, it's not there yet. It requests messages from the embedded database, places retrieved messages to the in-memory store, and returns them back to the frontend. Feeling some disturbance in the forest, Luke opens the messenger tool and uses his Jedi powers to route his getMessages request to another yellow replica. The processing of the yellow replica is roughly the same. Messages are requested from database, place it to the in-memory store, and returned back to Luke. Caring about Luke, Leah asks him to go for a lunch. That means we have the add request arrived to the blue replica. Application inserts this new message to the embedded database and puts it to the in-memory store. The state of the in-memory store is now like this. All done, the message is sent. Luke get push on his phone, requests fresh messages from the yellow replica, and the application takes in-memory state of conversation, and Luke gets a stale state. No lunch. The galaxy is in great danger now. This is where the data freshness plays important role. Adding the new message blue replica should somehow notify other replicas about it, so they can refresh their in-memory state. We could use the cluster topology information like we did before for client routing, determine all replicas which could possibly own this conversation, and notify them about the new message by sending a special edit request. Then the application would place a new message to the local replicas in memory state. It is not stale anymore, and the galaxy is safe now. It is not. The problem is that this edit request is being sent from one replica to others over the network. So all 7 failure scenarios start to apply here. So this edit request could be delivered only to some part of replicas. The other part could not have it delivered for a long time, depending on what happened to the particular replica. It could possibly crash the hardware failure or for a long time. Let's take a look how Cassandra is about to handle the same situation. We execute the insert statement. It determines all updating conversational replica nodes, builds an update request, the mutation in Cassandra terminology, and tries to send it to all replicas over the network. Because the messenger application and the Cassandra database node share the same process, this mutation message can be delivered to all replicas due to same failure reasons. In this case, Cassandra stores undelivered messages to the local persistent store. Whenever the yellow node is back online, all these stored mutation messages are sent to it. This is called hinting. Usually, these hints are stored only for a limited amount of downtime. Otherwise, healthy nodes could run out of disk space, storing all to be delivered hints for a single node's prolonged downtime. So there are other ways of restoring consistency between replicas. They include the read repair, a process of comparing results returned by several replicas on the same query. If there are any inconsistencies detected, a mutation message is sent to the stale replica. And yet another final way is the streaming repair, a background batch process of iterating and comparing through data stored on all replicas, when mismatched ranges of data are exchanged between nodes. Because the volume to exchange could be large, new data are exchanged in the form of the stable file over the separate streaming connection, instead of sending individual mutation messages. These consistency support methods are hard to implement and debug, so it could be wise not to re-implement them all for the in-memory store. So what could be much easier is on receiving the fresh data by the database engine by either normal mutation, hint, read, repair, or streaming, the database code could notify the application logic, which then refreshes the in-memory state to include fresh data. I mean, we define this apply mutation listener interface in the database engine code, implement it in the application code, and have it called back by Cassandra. This functionality is not implemented in Cassandra currently, so we have to extend it by ourselves. Luckily, there are only 2 components to extend. All mutation messages, regardless of its source, normal, hint, or read repair, come through this method. The mutation parameter here is the mutation data with the fresh data for several tables. So we can take data from there and pass it to the listener. On completion of whatever SS table streaming, this on completion runnable is run. We could take SS tables from one connection, iterate over them, reading from it, and send fresh data to the listener. Consider the same case. The mutation message can be delivered, but not due to this network failure, but because the yellow replica server is crashed and gone to reboot its operating system. Its in-memory state is vanished. Now hints can't help. Hints contain only the fresh data received by the rebooted node, but getMessages need all data lost from the in-memory state and the fresh one. We could get the vanished state data by retrieving it from the database. This retrieval should be performed for every conversation which was active before the replica rebooted. And this should lead to the massive spike in amount of read requests right after the node is started. And because reads are served by a quorum of nodes in Cassandra, some network communication occurs for every read. There is a strong chance of catching the cascading failure of the whole cluster. How to fix this? One could use the well-known strategy on having a periodic in-memory state snapshot to a persistent store, combined with the Pareto head logging of changes between two consecutive snapshots. But again, thanks to the embedded database code, we could avoid re-implementing this from scratch. We create the cache key space with the local replication strategy. This strategy basically instructs Cassandra not to replicate data on cluster and store it only locally. Then we declare the messages snapshot table here, and whenever data is put to the in-memory store, it is being written to this table. If data is evicted from the in-memory store, it is being deleted from this table. So this table now stores the copy of in-memory state. On node start, it loads this state by executing this simple select query. This loads a lost state from a persistent local storage, and hints apply the fresh data a bit later. This select query works fairly fast because it iterates sequentially over locally stored data, but still it takes some time. And this waiting time should be avoided when starting a node normally due to an application new version deployment or maintenance. Loading state from persistent storage can be avoided by using this shared memory to store the in-memory state. A shared memory is not cleared only at the application restart until the machine is not rebooted. The simplest way to employ shared memory is to open this file. It's better to use a memory mapped file, of course. For Java, ready-to-use structure could be used. They are all implemented in our OneNeo open source library. The sharded memory map and its subclasses provide the necessary functionality. In Linux, the TMPFS file system usually is mounted under a dev SHM path. It's fine. We also use huge TLBFS file system with larger 2 MB pages. This allows to lower the number of TLB misses accessing shared memory and can conserve a bit of CPU cycles in heavy loaded cases. This makes things much faster. Starting the node with the shared memory map does only a quick sanity check. The start became so fast that part of requests hit the just started replica before other replicas sent all pending hints to it. And Luke could get stale data from the memory store again. This is because the hints delivery is asynchronous in Cassandra, but this is by design. Cassandra reads data from several quorum replicas every time, comparing results returned from every replica to others. So it can detect and throw away stale data before returning them to client. This heavy read makes the hinting an optional optimization, which is not strictly necessary for the consistency. The messenger application gets 15 times more read requests than writes, so it's better not to use such heavy reads for its consistency resolution. So right after initializing the in-memory state locally, we start the embedded Cassandra cluster services and waiting for hints to be delivered from the healthy nodes. Only after all hints are played, the application is allowed to start to access requests. This waiting looks like some kind of distributed coordination. We tried several strategies, and now we made use of the simplest one. The static node periodically resends a check for unplayed hints request to all other nodes. It then waits until all nodes confirm they have no more hints to play, and then suggests it is in a consistent state. So that's all about in-memory stores. In today's talk, let's have some summary on them. In stateful microservices, the in-memory store shares the same process with the application and the database node. It is custom, and application logic is implemented on it. Application objects are stored and manipulated in memory of the application service. This allows to avoid unnecessary costs associated with dedicated remote caches. Marshalling and unmarshalling overreads are now easily avoidable by careful application coding. Network costs are not applicable at all. The data freshness is the hard problem for remote caches to solve. We solved it by extending the embedded database engine code with mutation listeners. They allow us to add an application logic on a new or updated data, so we could guarantee an in-memory cache data is as fresh as it is in the database. The state loss problem should be addressed for any in-memory store. We solve it by replaying in-memory updates to the local database table and use shared memory to avoid loading a multi-gigabyte state from the persistent store on every normal restart. In stateful services, in-memory caches could have the same consistency guarantees as the database. This is very hard to achieve for remote caches. Now, let's see how effective the implementation of getLastMessages request processing could be. This request retrieves a single freshest message for a list of users' conversations. To handle this request, a list of messages has to be retrieved from many conversations. Different conversations could be owned by different application service instances. There are no single instances owning all data. These message lists should be retrieved mostly from inactive conversations. As we can see here on the screenshot, only one from many of conversations is selected and active. And this means that these conversations are absent from the in-memory store, and there is no point to load them there. Inactive conversations remain so most of the time. Messages of inactive chats are highly likely consistent across replicas. Most of consistency procedures, hints, and repairs have their chance to run. Whenever inactive conversation becomes active again, it would be loaded to a memory store. Probably we could make some optimizations based on this knowledge. We'll see. For stateless service architecture, we would have it implemented this way. The client calls getLastMessages in the microservice, and then it would retrieve message lists from memcaches for every active conversation, and then from persistent database shards for inactive ones. Contrary, in stateful services, there is no single instance to call. Any single instance is required to make a network request for all data not owned by it locally, and this implies costs we are trying to avoid. The effective way is to have getLastMessages implemented on all participants here. Microservices have their own implementation, and client has its own. Client's implementation uses the service cluster topology information and splits list of conversation IDs to several sublists. Each sublist contains only IDs of the conversations owned by a single service node. Then it selects the replica for the first sublist and requests last messages from it. The same happens for the rest of sublists. Service instances process these requests, each for its own subset of conversations, and return only a part of response to client. A client waits for all necessary partial responses from the services, collects and merges them into a full response. It is essential to call all necessary replicas in parallel to keep duration of the request processing short. We also do here a speculative request to several replicas of the same subset of keys to avoid sudden single replica slowness to influence the whole request processing time. This is called speculative retries, and you can find more on this in my distributed systems talk. On the server side, getLastMessages also has some interesting topics to discuss. Let's start with implementation this straightforward way. First, the in-memory store is called to retrieve last messages of active conversations. Then the embedded database code is called to get freshest messages of inactive chats. But Cassandra is a distributed database, and this means that it makes numerous network requests for data from several replicas to build a consistent response. But we know that data consistency is not that important for inactive applications. Replicas are highly likely own consistent data for them, so we would skip this consistency resolution and additional network communications, retrieving only local copies of replicas' own data. There are no standard way to skip the replica consistency resolution using database client drivers, but on embedded Cassandra code, we could call not only public API methods, so we could call local reads using this code. Here you can see a lot of some magic, but this is all basically prepares query statement, binds statement parameters. The main difference is here, the execute locally is called. This allows to skip costs of network communication setup and execution. Now, we have to implement the last function for today's talk, the full text search. Whenever a user enters some text in the search field, all messages across all these user conversations should be searched and shown to the conversation list here. Of course, scanning for text through all messages of all conversations is not feasible, even if local reads are employed. A total data set of our messages is over 100 terabytes, so even 1,000 machines cluster can't make it fast enough. So we have to build an inverted index using, for example, Apache Lucene. A single large inverted index containing all conversations would not work. This is another interesting topic to discuss, but we are running out of time, so you have to believe me here. Separate index per user would lead to unnecessary data duplication. Many users participate in any single conversation. So we have to build an index per every conversation. This index contains only messages of a single conversation. We build indexes upfront only for large conversations. For short ones, index can be built right before searching. So let's start with the straightforward implementation. Whenever a user adds a new message, the Lucene index writer add document is called to index it. And then we call Lucene to commit index. And this would not work. Too often commits leads in too often merges of Lucene index segments. These merges are both CPU and disk expensive operations. Contrary, do not calling index writer commit lead to too many open indexes because a single service instance adds hundreds of messages every second to multiple conversations. This could eat too much memory. A good solution here would be some background process, and this process would preliminarily merge new messages of a single conversation into a single collection as soon as messages are arriving, but not too often, to keep size of these batches moderate. And Cassandra has such a background process named Compaction. If you wish to know about this process in more details, here's the link for it. In short, Compaction merges different generations of data flushed at different time to persistent storage. Compaction is necessary for Cassandra to keep its data structure optimized. Compaction iterates over data to merge always in order defined by row keys. A single conversation is iterated at a time. Messages of the single conversation are iterated in order of their IDs. Compaction is managed by the class named Compaction Manager. We could easily extend it to call some listener interface which we implement in the application and call necessary Lucene indexing. And voila, now the stateful service can do the low overhead massive data processing. And this processing could be used in many other cases than iterating over the full dataset is necessary by an application. This is the last crazy trick for today, but not for the very last of all the possibilities. What I wanted to illustrate here is that embedding the database code allows for tighter integration of the application and the database, allows to extend the database in the ways necessary for the application, and allows for even more cost reduction across many aspects, not only related to request processing. So, we are now at the last section of today's talk, the production operations of stateful services. From the operations perspective, stateful services also have their own particularities. Let's look into them. The first problem to discuss is longer deployments. This is because of the longer start time of the stateful service. This is because stateful service embeds the database. This database has to perform a persistent data initialization at startup. The initialization time is mainly bound by the speed of persistent storage, speed and volume of write-ahead logs to replay. Another thing to wait for is the in-memory store loading, the lost state from the messages snapshot table we discussed today. This time is bound by the size of the state to load, frequency of change and eviction events, the CPU power, the number of key collisions. This could last for minutes and tens of minutes. The consistency wait time, we should wait for hints to be replaced by other nodes. This time depends on number of skipped mutations. So if deployment process stops and starts instances one by one, the total deployment time is proportional to the total number of instances and could easily last for a day for several hundred instance deployments. So to mitigate this, the deployment process should not be sequential but parallel, deploying multiple instances at once within a single availability zone. Our deployment process, for example, deploys a single instance first to make sure the new version is not broken, and the rest of instances of this availability zone deploy in parallel. Instances in the rest of availability zones deploy in parallel at once. This way, total deployment time remains constant regardless of the total instance count and depends on the availability zone count plus 1. The second problem is we restart database nodes more often. Well, we embedded the database to the application service nodes, so we restart the database nodes in each availability zone each time we have to deploy a new application version. Should we mitigate this? Actually, no. This is not a problem with today's fail-first databases like Cassandra. Moreover, this deployment actually tests an availability zone outage on every deployment in the controlled environment and during the work hours. So bugs in the availability zone outage or in handling of availability zone outage could be detected and fixed early before the real outage occurs. The third problem is longer scale-out. This is because data is collocated with the application, so to add the new instances to the application, data should be resharded, I mean physically moved over the network to the newly added instance. This problem is not specifically unique to stateful services. Stateless services require resharding to scale out their database and memcache components too. Still, they could avoid resharding for application logic-originated CPU or network-bound loads. This urgent need for the CPU or network consumption by application logic is often related to some new functionality. To mitigate this, capacity planning should be in place. The longer time should be taken into consideration, so an application could be scaled out before the load spike hits. To mitigate load spikes rooted in a new application functionality, feature flags could be used for a new code, so they could be employed to cut off the problem in code. There could be cases when application-sourced loads are unpredictable, externally rooted, and highly volatile, and the only solution is to have fast autoscale, which implies no resharding is possible. These measures may not help in this case, and sticking with the stateless microservices architecture may be a better approach. This is somewhat the development of the problem I mentioned on the previous slide. These problems apply only to applications which consumption of one of machine resources is much higher than others. To our experience, these cases are somewhat rare. Imagine a service which needs high amounts of CPU to do complex calculations over some small amounts of data. Such an application would consume all available CPU on the machine, leaving disks underutilized. It is impossible to install a fraction of disk into a machine, so the underutilized resources of the disk would be wasted. On the contrary, we could imagine an archive service doing very little processing over larger volumes of data. Disks of this service would be full of data, but a machine's CPU would be idle. Stateless services allow each component to be scaled individually, so these imbalances could be mitigated by scaling out stateless service component more for the first application and scale down the database more for the archive one. For stateless, this is not possible. State and application logic are collocated. These imbalances could be mitigated by employing containers and orchestration management systems. They aim to balance resource utilization across the fleet of the machines automatically, allocating different containers with different resource consumption properties, keeping resources utilization of a machine uniform. A container with high CPU and low disk consumption would highly likely be allocated by orchestrator onto the same machine with a container having low CPU and high disk resource consumption. This would keep resources consumption of the hardware fleet leveled automatically across an organization. We used internally developed one cloud orchestrator for this, but there are several of others available. Kubernetes is one of the popular nowadays, but there are others as well. On the bright side, the diagnostics and support of stateful service are easier than for stateless services, because the application logic, the in-memory storage, and the database share the same process. It is much easier to diagnose and debug. Setting a breakpoint somewhere in the application logic, one could easily track down the problem to the root of internals of the database, and even down to the operating system kernel. Running the profiler, one could track down performance problems more easily. Here you can see, for example, profiler run on a stateful service showing flame graph of the CPU time spent from the application code here down to in-memory storage stack traces and database engine operations here, as well as down to kernel space here. By the way, this flame graph is built by the async profiler, one of open source projects we originally developed within OK.ru. It's low overhead, so you can run it safely on Java servers in production. For stateless services, a memcache and database run on remote processes. Profiling and debugging an application often can't show the root problem. Running separate profilers on a memcache and a database can show the application context. Most of stack traces start somewhere on network request dispatcher, hiding the maybe the root of the problem, application-specific information. So diagnostics often end up on custom database diagnostic tools, on even random guesses if tools are inadequate or does not provide the necessary details. And now we're at the final slide of my talk. Stateful microservices are more effective and reliable, and application logic shares its cache and database in the same process. There are no network between them, so avoiding meshing and network implied costs. The custom implementation of in-memory store avoids overage cost. Stateful services have an in-memory state consistent with its database state, which is hardly achievable with remote caches. This is not so hard to implement, it's not so hard to implement it having embedded modern distributed fail-first database. On Java, the OneNeo library could be used to build custom in-memory stores. Stateless microservices was invented more than a decade ago. Problems to which stateless was aimed for could be solved now in new ways. There was a lot of progress during the last years in distributed databases, which with seamless auto-sharing support and designed to be fail-first from ground up. Containers and orchestration systems are good at the process isolation, and the hardware machines automatic utilization leveling this allows us to avoid externalizing an application in memory and persistent states in remote systems and open a road to build more effective and reliable services. Thank you very much.
Wow. Cool, Oleg. Thank you for your talk. It was really great. In English, please.
Hi, everyone.
Thank you for your talk. It's really a controversial topic because stateless microservices has been on a hype for many, many years. And now you're talking about stateful microservices. Yeah. So I'm waiting for questions, and I can't see anything yet. So I have my own questions for you. Um, can you please give some examples of production services at Odnoklassniki which implement the approach you described, like real services?
Well, the best example could be very first stateful service at Odnoklassniki was the likes microservice. This service is very loaded. Currently, it serves about 5 million requests per second. The like service
Wow.
is this service which stores all the likes of the topics on the social network. So it has a lot of data. And when I first started I was started with this service to solve its problems because it was made as a classic microservice and was really it was not able to handle the load, so I had to invent something new, and this pattern was born. And now it's widely this pattern is spread very widely inside of Odnoklassniki. Messenger I made a talk about is one of the examples. Even our internal blob storage system stores and handles its metadata in such a stateful microservice, but it is kind of very technical one, storing the meta blocks information and the location of blocks across the large infrastructure, which stores multi-petabyte blobs, including videos, music, and photos.
Oh, I see. Wow. And so the likes cluster is the largest one, right? And do you remember how many nodes does it have, and what is the replication factor?
The likes cluster is not the largest one. Yeah, it has only 96 nodes currently. It's not the machines; it's instances in our private cloud. The replication factor is 3. We just because it is Cassandra, and the 3 is the minimum replication cluster, which is viable in quorum systems. The largest one, the largest cluster is the messenger service. It's about, I believe, more than 200 nodes at the moment.
You mean 200 nodes in one availability zone, or combined with all the?
No, it's combined over the.
Yeah.
In 3 availability zones, so it's about 100 per zone.
Yeah. Okay. And okay. And in the first part of your talk, you mentioned numerous performance costs due to marshalling and unmarshalling and networking, and so all these costs were eliminated. And but you didn't tell anything about RPC implementation being used at Odnoklassniki, like because client applications they talk to the services through some RPC. Can you clarify it and tell something about it?
Well, RPC service across Odnoklassniki is partly open sourced. It's now a part of the OneNeo library, and I posted a link on the OneNeo library to the chat. So there are a lot of different systems combined there in one library, including the shared memory and the RPC framework. The RPC is somewhat very efficient because it allows up to 30%, only 30% of the original Java serialization traffic if you use, for example, Java RMI to pass Java objects. And this allows you to conserve 2/3 out of traffic. It has very efficient network subsystem, Java serialization subsystem. It's very compact and very efficient. And even if you write the serialization by hand, won't be faster. So take a look at this library. It's in the very heart of Potato. So it's very fast. And of course, yeah, this is only the core part of the library, because we have more layers which provide monitoring and statistics collection and so on to integrate the RPC framework in our infrastructure.
I see.
But
okay.
So they are somewhat very internal. Yeah, but these layers are somewhat internal to our infrastructure. So
yeah, it looks logical.
We didn't publish
it. Okay. And so just talking about some possible drawbacks of the approach. So in your approach, still we compose multiple components into a single process, right? We have some application logic, remote interface, cache, embedded Cassandra, and it runs in a single process, like each node is a single one. And so you mentioned canary releases, different availability zones, feature toggles, etc. But still, if any of the dependencies is buggy, then we will have to roll back whole service. Don't you think it is a drawback of the approach, actually? Because as you said, in stateless microservice world, you can just roll back each different part separately. Thank you.
Yeah, this is the same problem that actually arises in stateless services as well, because you can actually roll back the stateful service just like you roll back the stateless one. It just takes more time. For the time is spent on starting the service. Actually, the start time of the service is longer than stateless one. So to fight the time, to fight the time, we have a hot code replace process in place. This is the actually, it uses the standard ability of the Java virtual machine to hot swap the code it runs on the running process. Of course, this it is not possible to make very large changes in the code for the hot swap, but still, in most cases, to do a hot fix, it is enough. Of course, the automated testing and automated deployments and so on, the automated processes of deployments are very important too, to avoid hitting the code, hitting the buggy code in production. And of course, the monitoring part is very important too. We have the automatic anomalies detection system, which helps us to identify buggy implementation much earlier than it becomes a real problem. So we can mitigate it before it becomes a real problem. So these common parts are, I believe, must be in every organization which does the microservices anyway.
Yeah, I totally agree. And so talking about buggy parts, so we are developers, we are humans, and sometimes we deliver the code that starts corrupting the data it touches, because now we have a database embedded. And you know, if you tell any sysadmin about that, he will become mad, you know, because they got used to some backups to restore the database and roll back previous versions of data. And so could you please delve into recovery mechanisms we use at Odnoklassniki for this Cassandra data, because now it's much easier to corrupt the data and deploy some buggy code.
No, it is not. Actually, it is not the unique problem of the stateful services. Having stateless services and omitting, for example, the bear clause in the SQL delete statement, you can corrupt the external database data as well. So this is not the case not the property of the stateful service. This is generic problem of corrupting the data. And so it is to mitigate this, you should back up your database. The other side of backing up the databases in Odnoklassniki is that the amount of data and number of databases is very large. And we prefer not to back up the data in classic way. Instead, we do snapshots of the Cassandra database, and Cassandra allows to does snapshots of database very fast. It's a matter of second or even under the second. So the state of the database is being snapshot, and then this snapshot is being copied to the archive disk, which is located on the same machine, or is located in the same instance in the cloud. So it's always the separate disk. So in case of some corruption sourced or rooted in the programmer's code due to bug, we can restore the state of the database from the snapshots and applying the write-ahead logs of Cassandra from it. Applying, I mean selectively, not using all the mutations stored in the write-ahead logs, but some of them. So yeah, this is the backing up the snapshots onto the same machine is we do, and this is just because we don't need backing up the database because of corruption introduced due to hardware failure. For this, to mitigate the hardware failures, replication factor is in place. So we always have active replicas in 3 availability zones. So if in any availability zone the hardware is failed, we just do a node replace onto another machine. So it uses the 2 replicas of the 2 live replicas to pull data from onto the new instance and run that. But to mitigate the bug, we use the bug source corruption. We use the local snapshots and local copy of snapshots to archive.
Oh, I see. Right. Thank you. Yeah.
All right, folks.
I think we are running out of time. Yeah.
Kinda. Oleg, Vadim, thank you very much. Thank you for your talk. It was really.
Thank you all for watching.
Yeah, by the way, I remind you that you can ask more questions to Oleg and Vadim in Zoom chat and webinar. Please follow the link below the player. And see you there. Bye-bye, folks.
Yeah. Thank you.
Bye.
Goodbye. Let's move to Zoom. Yeah.